Damped and forced harmonic motion, example 2. A particle of mass 2 kilograms moves in a horizontal straight line. At time t seconds, the displacement of p from a fixed point O on the line is x meters and the velocity is v meters per second. A force of magnitude 8x acts on the particle in the direction PO, and the particle is also subject to a resistance of magnitude 8v. The particle starts at O with speed 5 meters per second. We want to show this differential equation. So this is very similar to the first example. It's just the force is different. So if this is O and at some time our particle P is here, this is x, and so d2x and dt squared is measured to the right if x is to the right. But the force is resistive, and that force is 8x and 8v in this case. So that means we can write down that 2, remember 2 is the mass, d2x dt squared is equal to negative 8x, take away 8v, and remember that v is dx dt. So bringing everything to the left, we've got 2 d2x dt squared plus 8 dx dt plus 8x is equal to 0, which gives us d2x dt squared plus 4 dx dt plus 4x is equal to 0 as required. Find an expression for x in terms of t and identify the type of damping. So in other words, we want to solve this differential equation. So auxiliary equation is m squared plus 4m plus 4 is equal to 0, which gives us that m plus 2 all squared is 0. And so we have a repeated root of m equals negative 2. That gives us a solution of the form ae to the negative 2t plus bt e to the negative 2t. Now we can use the boundary conditions. So x is equal to 0 when t equals 0 gives us 0 is equal to a. So we now have that x is equal to bt e to the negative 2t. Now we know that dx dt is 5, so dx dt, we need to remember this is a product. So this one times this differentiated gives us b e to the negative 2t. And then we've got this times this differentiated gives us negative 2b t e to the negative 2t, and then that's equal to 5 when t is 0 gives us b is 5. So we finally have that x is equal to 5t e to the negative 2t. Now we know that when we get equal roots as we did here, remember we found that m was equal to negative 2 and negative 2, that is critical damping. When I graph this, this is the shape I get. In the introduction, the critical damping was the red. So you won't always get exactly this type of shape. It depends on the boundary conditions, the shape that's actually produced. And when we do the next example, you'll see that we have a heavy damping example that gives exactly the same type of shape, but it's a bit lower. So the shapes can actually be determined by the boundary conditions that we're given to start with, and this is just a guide. Coming to part C, we can see that there will be no oscillations, so there's no point in even thinking about period. You can see that this is just going to asymptote immediately.